And we'll look at this. There's something that's covered in here too that we're going to cover in sensors that vary their resistance. So we got sensors that vary their resistance with what they measure, but then somehow we got to take that and convert it over to either a voltage or a current. So we know what a sensor is now, right? And then we went over the many different types of sensors. And then we're going to look at load sensors, and we'll look at bonded wire strain gauges and also semiconductors. But one thing we have to understand is that these are devices, bonded wire strain gauges, and some of our temperature sensors. A lot of our sensors vary their resistance with what they measure. But the problem is normally what we want to do is we want to get this into a voltage, right? You understand? So if I come over here and do this right here and change this into this, and then I put this across a 12-volt source, if I put a meter over there, what would it measure? Guys, what would it measure?
Oh, really?
Well, one thing, if I put my resistance meter into a 12-volt circuit, odds are you're going to mess up your meter. Now, your very expensive meters are usually pretty forgiving. You got one of these cheap Harbor Freight meters, might pray for you because that sucker might blow up in your hand. So we never, ever, 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 ever use a ohm meter in a power circuit, or try not to. Okay. So what would it measure? Yeah, it's going to measure 12 volts. Well, what if I set this to 5K? What's it going to measure now? It's going to measure 12 volts. Well, what if I set it to 10K? What's it going to measure? It's going to measure 12 volts. But what we're doing is we're varying the current, right? You understand. But most of our sensors, we use a voltage because voltage is so easy to measure. So to measure a current, I got to put something in series. So normally what they do is they'll come over here, even on current loop, they'll run it through a resistor. And then they'll come over here and they'll have a differential amplifier that basically measures the voltage drop across the resistor caused by the current loop. So to measure current, we have to put something in series with something, right? You understand that. To measure a voltage, we just got to go across, right? You understand that. So this is why by far, even current loops have to be converted to a voltage before they're processed. So we use current to transmit it, but then we use voltage to do what? To process it. So what I would do is I would come over here and I would take this resistor, I would put a fixed resistor in series with it. And then my sensor maybe be down here. And then now I could take my voltage drop across the sensor. Okay, so if this right here is always 10K, and then I set this right here to 1K, then that sensor is going to drop 1/11 of the voltage. If I set this to 2K, then this resistor would drop 2/12K, or 1/6 of the voltage. So what would happen now, since I've got a fixed resistor, when I vary the resistance, I vary the current. The voltage drop across the fixed resistor goes up and then or down depending on my unknown. So that means if I'm going to take a sensor that changes its resistance with what it measures, I can just use a fixed resistor, right? You understand that. And then now I have a sensor that gives me a voltage that's proportional to a resistance. And we could vary the size. So right here, when this goes down, the voltage goes down. When this goes up, the voltage goes up. So that means my output voltage would move in the same direction as my sensor. I could come up here and do it like this. Put my sensor right there. Put my fixed resistor right here. And then take my sensor right there. So here, when this goes down, this goes up, and when this goes up, that goes down. So if I need something that's moving in the opposite direction, all I have to do is just rearrange or where I put my fixed resistor. Now the problem with this, if I've got a weight something that's measuring a weight, it's going to have a resistance, even when there's no weight on it. So we're saying, okay, there's no weight on the sensor, but the sensor always has a resistance, right? Understand? So that means even though I put no weight on this thing, it might have a resistance of 1K. If it has a resistance of 1K, it's going to drop a voltage. So I get a voltage output even though there's no weight on my scale. Now that would be awful. Me paying for something. So I go up there to the grocery store and they weigh my fruit. Well, what's on top of that weight sensor? Well, you got a weigh scale. You got we call it the weigh bridge. You got the metal plate that's on there. And if they didn't do something, then I would be paying for the weight of that, right? So I need to have some way. So what do they do on these big hanging scales? Well, they have a 0. What do you have on your scale? If you got a floor scale, you have a 0, right? You understand? So you come in there and you set 0. If you can set 0, but you're doing it manually. Now I've got digital scales now. So the first thing it does is when I turn it on, it goes through a little calibration and it knows I'm not standing on it, so it reads what? Reads 0. In fact, you have to do it twice. You stand on it, it'll come up and give you an error. Then you step off of it and it'll 0. Then you step back on it and it'll give you your weight.
So we have tanks that have 3 load cells, but the summing junction box had 4 connections for 4 load cells. We only used 3. So it was calculated. We never cut the wire for the one.
You shouldn't have. You should make it.
Yeah.
It wasn't even hooked up?
No, it was hooked. We had 3 hooked up to it, but it was still trying to calculate for 4 in the road ring. And the butterfly valve was closed.
Shouldn't have.
Jamming the lines up. Nobody figured
Shouldn't have made any difference if that was the way it was. I don't know what you're saying. It wasn't used. It wasn't hooked up to the weight, so it was given 0.
We only needed 3, and then the summing junction box was 4 connections.
So it sounds like one of the load cells were bad to me. Because normally, if you got 3 load cells or 4 load cells, and you got one weigh bridge, well then it comes in and sums all of them together. But if you got 3 load cells, and this guy over here is not, it's always giving me a 0, that would give you a problem. So either it was bad or, well, either it was bad, the load cell sounds like it was bad to me. So it was giving you an erroneous, and it was still being added in. You can take it out, it doesn't make it, and then recalibrate it for 3. But then the bridge is not as sensitive as it would if you had 4.
We had the fill cycle too.
Believe me, I worked on electronic scales that was one of my jobs. It was pretty interesting. But what we're trying to do is I need to be able to establish what 0 is, right? Does that make sense? And I need to be able to do it electronically. So that means they bought a new truck scale out of it. We had a big, I think it was 180,000 pound scale. It was a big truck scale. And they bought an electric scale out there. And it was the lime scale for bringing in lime. And what they do is they bring the truck in when it was full and they would weigh it. And then they'd go and dump their lime and then they'd come back and weigh it again. And it would give them their net weight automatically. Well, they bought this electric scale without an auto 0 on it. So that means when these lime scales would move back and forth, they drop material on the scale. And the scales kept dripping up and up and up and up and up. And for some reason, these truck drivers don't like paying for more than what they got. So my task was to design an auto 0 circuit. That didn't work out really well. But what that was a problem where it didn't know, if the scale don't know what 0 is supposed to be, right? You understand? And it has no reference. So if I've got a load cell that's measuring a load, well, that load cell is always going to see something, right? You understand? Because it changes its resistance. So what a load cell does, a bonded wire strain gauge, What affects the resistance of a wire? What determines the resistance of a wire? Gauge, or the size, right? I don't know where my rubber band's at. Stranded, it usually has a smaller resistance than solid, but it's not enough to be noticed. The biggest advantage. So what's the biggest advantage of stranded wire? Flexibility. That's it. Flexibility. What's the biggest advantage of solid strand wire?
I think it carries more current, right? Well,
when you look at a wire gauge, it don't say 14 gauge stranded or ampacity. It don't say 14 gauge solid. It says 14 gauge.
Oh.
So what advantage does solid have over? Why don't we use stranded wire in our house? We use solid in our house. Because solid is easier to terminate. We can take solid, we could wrap it around a screw, we can tighten it down. So solid is hard, it's not as flexible, but it's easier to terminate. So I want to splice it, what can I do? I can just twist the dang thing together, put a wire nut on there, and it holds really well. So stranded is harder to terminate because when you try to put a screw down on a stranded, we call it bird caging. The wires try to spread out. If you lose one strand out of a stranded wire, you change the gauge. So usually to terminate stranded, we usually solder it and make it solid, or we put a terminal on it. We put a crimp terminal, where we crimp it down on there, and it's a round thing. You put the wire in there, you crimp it, the strands can't go anywhere, so you don't change the gauge. So the biggest disadvantage of stranded is harder to terminate, but it's more flexible, right? You understand? So there's your two. So now you know. So solid strand, I can just twist them together and tape them, right? You understand? Stranded, I have to put some type of terminal or something, or use what they call a compression. So if you're over on the manufacturing line, when we tighten those stranded wires in, they're inside a little box. And we're literally pushing down on that box, and the strand, even if they fan out, they got nowhere to go. So we don't change the gauge of the wire. Those kind of wires don't work real well with solid. Solids we just wrap under a screw, right? Understand that? So how can I set zero with this? Well, they came up with a ingenious invention, which we refer to as the Wheatstone bridge. So this is the Wheatstone bridge. And of course, this is, the name got this by the guy that figured it out. But what we do is we use two strain gauges, and they're nothing but wires. And why do we use two? Well, what we're going to do is that when we look at the one on the left, it's set in the direction of forward. The direction of forward. So what's going to happen on this one is when the force is applied, it's going to literally stretch this thing out. It's either going to compress it or it's going to stretch it out. And do I have a rubber band? Everybody's seen a rubber band. So think of the rubber band. And I've got it. Well, when I pull it, what happens to the gauge of it? Not only does it get longer, but it also gets thinner. So if that was a wire, what would happen to its resistance? Well, it's getting long, the length is increasing, and the gauge is decreasing, which causes the resistance to go up. If I take the rubber band and push it together, it gets what? Fatter, which means it's also getting shorter. Well, if it gets shorter, what happens? The length of the wire goes down, and the size of the wire goes up. So the resistance goes down. And this is exactly what it's trying to do. So what we do is we take these gauges, and we literally mechanically bond them to whatever we're trying to build the force on. And When those metal band, when those things expand, it used to amaze me, like, James was talking about load cells. We had some 100,000-pound load cells. And them suckers were chunks of solid metal. Big old thing. And then they bonded the wire gauge, the strain gauges to the side. And what would happen is big old trains would pull up on that. And it would literally cause that big chunk of metal to compress. Right? You understand? Which would cause the strain gauge to compress, which would cause the gauge to get bigger and shorter, and the resistance would go back. So all we've got to do, whatever we want to measure, we just put one of these things on. The problem is, so what does the strain gauge do? Well, when we either change the length, and we change the size. Now we can't change the material, that's no big deal. So what's the other thing we got? So what's the four things that determine the resistance of the wire? The size, the length, the material, and the temperature. So this is the guy we got to worry about. So the strain gauge changes its size and changes its length. Now, once they decide a material that they're going to make the strain gauge out of, then that's a constant, right? So what do I got to do? Well, the problem with temperature, when a metal heats up, its resistance goes up, and when the metal cools off, its resistance goes down. So I don't want my scale to weigh more in the summer or less in the summer than it does in the winter. So what we do is we put another gauge in there that's opposite of the force. So this is the spring action, right? So what's going to happen here is what happens to the gauge of a spring when you spring it out. The gauge don't change and the length don't change. So one of them set as a spring action, one of them set as a gauge. And they're mounted right by each other. So what happens if the temperature goes up, the resistance goes up here, well the resistance down here goes up exactly the same amount. It's the same gauge made out of the same material, the same length, right? Everybody understand that? So one of them's in there to compensate for temperature. One of them we call the active gauge. This guy's in there to change resistance and weight. But they're also changing the resistance and temperature. So what we need to do is understand how this thing works. So I'm going to redraw it, and I don't want a custom slideshow on it. But I'm going to draw it like a series parallel circuit. So this is a Wheatstone bridge right here. What I'm going to do is I'm going to put my voltage on the outside. So let's say we put a 10 volt supply out there. Let's say this is 1K, this is 1K. Let's make them all the same. And I'm going to put a voltmeter right there. Well, Kirchhoff's voltage law says, so this is a series circuit. Now my voltmeter's got a real high resistance value, so it's not going to affect the grid. It's not going to So we're going to assume that that meter has infinite resistance. It's actually got about 10, 20 megohms of resistance, which is not going to affect the circuit at all. Okay, guys, what would my meter measure? Well, both of them, Kirchhoff's voltage law says the sums of the voltage dropped in a series circuit has to equal the same. Another thing we learned that if you have two resistors of the same value in a series circuit, they will drop the same voltage. I mean, this guy right here is going to drop 5 volts. So if this is my reference right here, this is going to be sitting at plus 5 volts. This right here is going to be sitting at plus 5 volts. What's my meter going to measure? So what does my meter measure? My meter measures a difference in potential. Right? So this is a big problem that students have. Just like I said, if I came over here and looked at two devices, over here I put my meter on plus 12, and over here I put my meter on minus 12, what would my meter measure? A lot of people say 0, but it is a difference in potential. So over here I'd say plus 12 minus a minus 12. What do they tell us to do? They tell us to change the sign and add. So my meter would show 24 volts. Over here I'm going to say, okay, plus 5 minus a plus 5. What's my meter going to show? 0. There's no difference in potential. Okay, y'all understand that? Yes or no? But most people come up here and they'll say plus 5, and we say, okay, what's the difference in potential? And for some reason it pops in their head 10 volts because I got 5 and 5. And they're adding them together. But as soon as I say a difference, what does it mean? What does that meter do? It subtracts the two. So that's why when I come over here and I'm measuring a voltage drop across a resistor, over here I might have plus 24 volts. Over here I might have 10 volts. And I put my meter right there. And this is a plus 10. What's my meter going to show me? It's not going to show me 34 volts. It's going to show me the difference in potential. How much did that drop, right? So I would say plus 24 minus a plus 10, and what's it going to show? It's going to show me 14 volts. So that's what your meter shows you. It shows me so how much current flow is in the meter? No current flow through that meter. There's no difference in potential. So what would happen if I came over here and changed this to my sensor? And then, so this is my sensor. And then over here, I make this a manual resistor that I can adjust. And I've got a strain gauge that always shows me 100 pounds, but 100 pounds equals the actual 0. Y'all understand that? Yes or no? So a strain gauge is going to have a wire has a resistance. So if I just came over here and took a strain gauge by itself and stuck it down here, right? Well, what's that strain gauge going to be mounted on? Well, it's got to be mounted on something that changes its shape with weight. So we put it, so a load cell, so we got a thing we call a load cell, which includes all this, by the way. So right now, I've got 0 weight on my weigh bridge. I've got a load cell right there. This guy here is going to show me some voltage. But that actually is supposed to be 0, right? You understand? But let's say this thing here is sitting here at 5K when it's got 0 on it. Well, what would happen if I come over here and adjusted this up to 5K? Well, we could calculate the voltage drop. This is going to drop 1/6. This over here is still going to drop 1/6. So my difference in potential would still be what? Would be 0. And now I'm getting 0 out of that. So any sensor that we have to have the ability to set a 0, then we're gonna have a Wheatstone bridge. Go ahead, Barry. We're using there's a neat formula for calculating the voltage drop of a series circuit. We know that, and this will save you tons of time. So look, I pull that right out of my head. It's called the voltage divider formula. What's the voltage divider formula, guys? And this is the voltage divider. What's the voltage divider formula? Anybody know it? So how much, this guy right here drops a certain amount of voltage, but the voltage this guy drops is relative to the other resistors in the circuit. So the voltage divider formula is, commit this to memory, VRX, so this is the resistor I want it to drop around, is equal to RX over RT times DS, the source of it. So I could calculate this right here. So VRX is going to be equal to what size is the resistor? 5K. What size is the size I want? So I got that. Huh? Yeah, 6K, right? So I got it wrong, Barry. Thank you. What's going to cancel out? So I gave you the voltage drop across that resistor. This is actually what? 5.6. Thank you. And then we would do what? Well, VS don't make any difference. Y'all understand that? So 5.6. Thank you very much. Now the 1K is going to drop what? 1.6. The 5K would drop 5.6. Well, if this guy's dropping 5.6 and this guy's dropping 5.6, that means the voltage between, we'll call it A and B. What would my meter show? My meter's going to show 0. Everybody understand that? Because they're both up the same. So what we have the ability to do, Wheatstone Bridge, is we can use a sensor that varies its resistance, but it gives us a resistance even when it's supposed to be measured 0, right? So I got a temperature sensor. We call it a thermistor. Thermistor. So what do you think it changes? Changes its resistance to temperature. Well, by George, it's going to give me a resistance at 0 degrees, right? So, but if we use that in a Wheatstone Bridge, what can we do? We can set 0. Now, what we can do also is I can come up here and do this. So what we're doing here, though, is we're coming up here, and this one is varying with temperature. So this is my compensation. This one varies with force. So it means if this right here goes up 1K, this guy here is still going to go up 1K. And so understand that. It's because they're mounted together. So what's happening is your compensation is in there to compensate for temperature, and then your active gauge is in there to compensate for weight. And then we zero it out by the meter. So we don't zero it out by the bridge, we zero it out by the meter. So we take the combination of this, and we call this a load cell. So the load cell has its 2 voltages we call excitation voltage, which would be this guy, and then we get this output right here that comes into our scale. We get 2 wires coming out. So every load cell will have 4 wires. The bridge is built into the load cell. So you see 4 wires on what we call a load cell. 2 of them is where you put your excitation voltage, usually 10 to 15 volts, and the other one 2 would be the actual differential output. And then this will come into our scale. And then we zero the indicator. Does that make sense? So we don't set 0 with it on bridge. But my 0 circuit for USL was a very interesting circuit. Huh? Yeah, the problem we have with load cells, of course, is these little old tiny strain gauges are extremely small. And the wires themselves are extremely thin. And so if you got any big, like an EMI pulse that comes through, it's like people wanted to know why does capacitors and outside air conditioning units, why does capacitors keep going out? Well, by George, they're outside. And they're outside, where we got lighting and all that other kind of stuff. So that's why they go bad. Well, anytime you get into an extremely noisy environment like U.S. Steel, y'all guys just don't understand. If you've never worked at a steel mill, you just don't understand that environment. It's pretty nasty stuff. There's a lot of stuff going on. There's a lot of mechanical stress on these devices, a lot of motion, and all kinds of ways that you can get yourself killed. You get one that can see all over yourself. This is a strain gauge. This is not really a good. Got these together. So we would take this and we would literally, we were using two, right? One of them would mount, and we would mount them perpendicular to each other. One of them would use for compensation, and one of them would use. So we put a meter across this thing, and we could literally put an ohm meter across this thing, and we could literally press it, and we can see the resistance of the tank. And you're gonna run into these. I mean, running into even in grocery stores, where they weigh. These things are extremely accurate. The biggest one we saw was the biggest one we had was 100,000 pounds, and it was on a railroad scale. And we only had one railroad scale that I worked on. It was an axle scale, so they didn't weigh the whole thing. They just weighed the axles. And what they do is they weigh each axle, and then they would add them together. Yeah. But out at U.S. Steel, we had several truck scales. That's the way I got my job. The scale stopped working, and I called in a company called Aero Equipment to come in and do the scales. And that was back if you brought an outside contractor in, you had to have one union employer with every outside contractor. They couldn't work on anything by themselves. Yeah. So that's back when the union was strong. Yeah. So I went and worked for this company when they laid me off when they built the pipe mill. This company hired me. So I worked on scales so I learned all that stuff. It's pretty interesting. It was so strange in that the way they troubleshoot these digital scales is they had drawers of spare parts, and that's back when most of the stuff was still in plug-in sockets, and that's the way they troubleshot. They would take if the scale the indicator wouldn't work, they'd start swapping parts until it started working, and they didn't realize that most of the time more than one part went bad. So what they ended up with is they ended up with bad parts in their good part bin. And then I came in there and I knew how to do it, and I amazed the guy. Especially when I brought my oscilloscope in there. He thought that was something. It was so funny. The guy that ran the company. Huh? I did. Because it looked kind of fun. It was but after that, I never.
You put some antennas out when you use it.
Oh, yeah. That guy, he came in, he called me one day and said, Rich, if you're going to cut down on your overtime, he said, you're making more money than I am. I said, well, I'll tell you what I do, Steve. I said, what do you want me to do? When I get 40 hours in, because you send me all over the place, do you want me to just leave? He said, let's try that for a little while. I was getting off on Wednesday. Yeah. So Steve finally called me and said, we can't do that, Rich. He said, whatever you need. Yeah. So this is basically the makeup of a load cell. So we have some sensing element. We got what they call shear beam. All we got to do is something that changes its shape with weight. So sometimes you'll see these things. They'll have a circle in them, and there'll be a big chunk of metal, and then they'll put the load cell. They put the strain gauges inside that circle. So we call them shear cells. So they'll come up here. They would hang weight on the end, and it would cause it to warp. You see these guys used in buildings, almost no buildings now that use metal structures where they're trying to measure the strain. They'll put these things in the building. They'll mount them on those I-beams from them. See how much strain goes through the wind and stuff. So, pretty neat. So we call this a load cell. The output, by the way, is usually rated in millivolts per volt. The ones we have is about 50 millivolts per volt. So what that meant was for 100,000 pounds, excited with 50, you decided it with 15 volts, then your transfer function would be, right? Your maximum voltage would be per pound or per weight would be, let me write this down. So let's say we excited it with 15 volts, and then the output, here's the excitation voltage right here, which is very standard on load cells, and it was rated at 15 millivolts per volt. Well, what that meant is that the maximum voltage you could get out of the measurement would be 15 times 15 millis. So what would that be? $225, wouldn't it? And 15 to 15, right? So that might be doing it. No. What is it? 15 times 15, 150. 225. I did hit it, didn't I? So this means the maximum the load cell would ever put out was 250 millivolts. So you can see these instruments had to be very, very precise, right? You understand? So if I had a 100,000 pound load cell, then that's going to be 225 millivolts divided by 1,000 pounds. That would be, this is milli, so we're talking about microvolts per pound. And this is differential, by the way. So we're sending two signals. We're sending the differential output, which used to really amaze me, how accurate these things were. So we buy and sell off load cells. Load cells are extremely accurate. We buy and sell off them. I was actually a certified calibrator, so I was certified to go out and calibrate scales that they sold. I never did go to Montgomery and take the test. They just gave it to me. So I got that twice. So these are basically, this one we got is a lot more running. These are what basically the strain is. This would be a very small load cell, and this would be the ratings that we have. So this guy was rated on 2 millivolts per volt. And we excited at 10 volts. So to get your maximum output, you'd say 2 millivolts times 10. And then you divide it by whatever you wanted to measure with it. So this thing is compensated between 20 degrees and 120 degrees. You don't say this is Fahrenheit. It's below freezing. Then it gives us our resistance, input resistance. But a lot of this, the only thing that we were interested in was this one and this one. And then the weight of the scale. And then they used to use multiple ones, and then they put them all over the bridge, and then you come in and you sum them together. So the problem with your scale is, it sounds like one of the load cells was bad. What did they do? Instead of getting a new load cell, they just took it out of the picture and then recalibrated the scale for 3.
We went and bought a bathroom scale, so that's how we did it.
But we had calibrated weights. The biggest ones we had were 500 pound weights. So we carried 50,000 pounds out in the back of the truck. Had a little crane assembly in the truck that we would set away from them. If you had a big scale, you'd have to do it 3 different spots. You'd have to do it on each end and in the center. And no matter where you put that weight, it was measured. If all the load cells were good, it was measured what? It was measured the same. So we had to diligently calibrate between sections. So it sounded like to me one of your load cells went out on you. You cut it out. Yeah, we cut it out. And then recalibrate it. But the bridge wasn't weighed perfect every time. It depends on where you put the weight at. Probably would give you a different way. So y'all pretty much will measure it at the same time.
Well, it was a tank. So it was actually centered.
Okay. So these are different types. So we have a big solid chunk of metal, which always amazed me how you can get something that's just a big chunk of metal that it would compress. And then the shear type, we usually mounted one side solid, and then we mount the load out here on the end. strain gauges for inside, on this one, I think they're right there. But sometimes you actually see it's all inside the circle. So what would happen is, it was hard to believe that that thing would be form enough to cause these strain gauges to measure that. Extremely accurate. Like I said, if you buy and sell off an electronic scale, it's going to have load cell. And a load cell is strain gauges plus the bridge, right? Resistors don't have to, in the bridge, they don't have to be the same value. But they have to be the same ratio. And then it would still be balanced. So as an example, if this is a 1K and this was a 10K, and then this down here was a 5K, and this over here was a 50K, it would still be balanced because the ratio is the same. This guy right here is still going to drop 5.6, and this guy right here is still going to drop 5.6. So as long as the ratio of the two sides are the same, then it's a balanced bridge. And what we mean by balanced bridge is the voltage drop, the difference in potential between this point and that point would always be zero. So when we do the bridge, it's not necessary to put the same values, it's just necessary to get the same ratio. That makes sense? Same ratio. Now in the load cell, they're going to be the same because the strain gauges have the same unloaded resistance. Except this one right here is the active gauge is varying its with force. This guy here is varying its temp, right? Does that make sense? And so what happens, it means now they compensate for each other. So strain gauges normally run in groups of two. To be extremely accurate, they need to be in groups of twos. If you don't run them in groups of twos, then that means it's going to change. It's going to vary depending on temperature too. We don't want it to vary depending on temperature. We want it to vary depending on a strain, right, a force. And we use it to change both the length and the size. And of course, we got that third thing in there we call the temperature, right? This is another one. Another way we can measure force. Don't pay attention to the figure numbers. I need to go take that out. So this is what we call a calibrated spring. So if y'all ever went, like right now in Walmart, you can go over to I think it's in Walmart. You can go over there to the vegetables and stuff. They've got a pointer scale hanging down. That sucker is not electronic, that sucker is mechanical. But what they do is they use what we call a calibrated spring, which means the spring is made so precise, it has a certain coefficient of expansion and contraction, right? So it takes the exact force to make it spread out as it does compression. Now if we can do that, if we got a spring that I can put a weight on and it causes it to spread out, if we can measure the amount it spreads, which is not hard to do, put a dial on it, and we can use that to measure weight. And that's exactly what those spring scales use. They're called spring scales because they'll see them in the grocery stores, or you go over to the vegetable market. They're still pretty common because they're very, very rugged. They're not electronic. They're pretty reliable. So a lot of times the grocery store will put it over there for you to use. Now the scales they use are electronic, and they use load cells. But the scales that you use are probably not electronic, right? So whatever we use to make this measurement, we can attach a linear geometry to it. And now what do we get? Well, now we get a voltage that represents that way. The next thing, guys, I do not bring it up. The troubleshoot class remind me. Then I'll bring it over next class. Is this next thing that we got? It's not very accurate, but it's extremely key. So y'all can see how this works. right? It's called calibrated spring or spring, these are called spring steel. And what advantages do these have? Well, they're real cheap, right? This is the same thing. So we can calculate, the thing here requires, this thing here will compress 60 pounds per inch. So if I come up here, if I can measure the inches, then I can measure the length, right? That makes sense? Okay. We take that and hook it up to the geometry. And of course, so when this thing moves an inch, that would be, so if it moved a half an inch, it would give you 3 volts, right? Understand? 60 pounds, so 30 pounds would give me, it would only actually press a half an inch, right? Yes, right. And then, of course, if I put 60 pounds, did I say like 30 pounds, it would press a half an inch, 60 pounds. 20 pounds, it would only do 2/6 to 1/4, right? So yeah, these are pretty cheap. They're called what kind of scales? Spring scale. The other type we have is what we call granulated or carbonated foam. So carbon is a unique material in that it's a semiconductor. So when you look at the atoms, so anybody know how do we classify conductors? What classifies them, or what makes them as insulators and conductors? What determines whether they're classified as insulators? Well, we use atomic bonding. Well, actually, most metals use what we call covalent bonding. Covalent. Yeah. Well, covalent is a technique where the atoms bond. One of the ultimate goals an atom tries to do is when we start looking at the shells of an atom, how far you go out determines the number of electrons it got. There is one unique shell, no matter how far it is out, it's called the valence shell. The valence shell can have a minimum of 1 and a maximum of 8. Now, if it's got 1, then it's very easy to bump that thing out. So anything that's got a 1 out in the valence shell makes it extremely good conductor. So that's your silvers and your coppers, right? Understand that. But anything that's got 8 wants to keep them because that's what it's looking for. So what it does when we say a covalent bond, these atoms come up and they start sharing electrons in the outer shell. And until the total number gets to be 8. And then it says, then it's back, and then it's balanced. That's called a covalent bond. Metals like to do covalent bonds. So anything that's got 8 out there makes a really good insulator because it's already balanced. So your rubbers and stuff like that have 8. So normally we say anything between 1 and 3, we use those as conductors, or can use them as conductors. Some of them we can't. Like hydrogen's got 1, but it's a gas, so it's hard to use as a conductor, right? So most of your solids that have between 3 and 1, we can use those as conductors. And then anything that's got 4 to 8, they can use those. 5 to 8. And we got these guys that's got 4. What are they? We call these semiconductors. So your germanium, your galliums, your silicon, and of course carbon has 4. The problem with carbon is that carbon is a very loose and light substance. And the problem with carbon is that if you compress it, its resistance goes down. And if you uncompress it, the resistance goes up. So for years, these were used as voltage regulators. They call them carbon pile voltage regulators. So what they would do is they would use a solenoid on the thing, and they would put it across a bunch of these carbon discs. And as the voltage tried to go up, the solenoid would spread them out and cause the generator output to go down. And if they tried to go down, it would go in and compress it. Well, somebody finally figured out and said, hey, we can use this to sense force. And then what we have is we have carbon impregnated foam, and then we put it between 2 metal plates of membrane. And when they something happens on this, it suppresses the foam and causes this resistance to go down. And we've got this, by the way. We made it. For years, we have, in digital or even in electronics, we have devices that are very sensitive to static discharge. So we call them metal oxide semiconductors or JFETs, if you've heard of it. So these devices, if you literally handle them with your hand, and you're at a different potential, you can cause them to go bad. So what they did is they wanted to provide these things where they couldn't build up a charge. So they would have this carbon impregnated foam, and they would just stick them in this thing, and that way, you couldn't get a difference in potential speed. If you picked it up, if you picked up the foam first, then you would get it the same potential, and you could do what you could do. So man, we got all types of carbon impregnated foam. So all we've done on our sensor basically is put some metal plates out here. And now what you can do is you can just take it and compress it, and you can see the resistance go down. And then you can uncompress it and the resistance goes up. Pretty nice, very cheap. But the problem is it's not extremely accurate because we have a problem with temperature. But we use these for years. Used to, when you walked into a grocery store, you had to open the door. Then they came up and put these dang pressure mats out there. That you did what? You stepped on it, all it was carbon, had two metal plates, had the carbon, and when you stepped on it, it did what? Because it was just changing. Of course, over time they would wear out, so what they've done now is replace the mostly with motion detectors, but there's still stores out there where if you ever go out there and they got two rails on the side and you gotta walk across that mat to open the doors, and they use these and they're still out there. Old school. Old school, yeah, but still. You worked out at US Steel. What's US Steel? Old. Well, yeah, it's new school and old school. So anytime they get something new, like a new plant, so when they put the arc furnace out there, it's gonna be state of the art. You get over to a pipe mill, it's gonna be fairly good, right? Yeah, and that's what we're saying. Normally, if it works, a company's got a tendency, if something's working, they don't upgrade. Yeah, and they do that. So as long as it's running. So you get at some of these old factories that keeps upgrading, you're going to run into stuff that's extremely old, and you're going to run into stuff that's brand new. So a lot of people don't like change. Well, they don't like change, but number one, you got a piece of machine out there that's making money. And it's going to cost you $2 million to upgrade it. You're just making money. I just did that. Yeah. So, we had worked at a place where, they had a bagging line that bagged Gerald's milk. I don't know if that's the Gerald's milk. It's the powdered milk that they sell at the grocery stores around here. Powdered milk. They had a bagging machine over there that I worked on. And it was ancient. It was all relays and screws and all that kind of stuff. They couldn't keep up with their demand, so they got a new line. And it was all electronic. They still ran both of them, so it was really neat. So you ran into old school and new school. You're right. If you got something that's doing exactly what it needs to do, then odds are a company's not going to do what? They're not going to upgrade it. So this guy right here would be considered more of a solid state type sensor. And like I said, I'll try to remember it. And that's the problem. Most of my stuff is over there. And then I'll have to bring it over here. But we have these, and we've actually made one of these, which is so neat. So that's basically the only force sensors or load sensors that we're going to look at. Do y'all have any questions on that? It was asked, by the way, Barry brought this up, and Thomas brought it up the other day too. I know the class goes to 1 o'clock, so it was suggested those people not be able to set the limit. And instead of trying to take a 15-minute break every hour, take a 20-minute break every hour and a half. You know, if you got a long break, is that okay with that? Sound good? I want to vote on it. All right. We'll start that.
I'll good.
week after next. I know, of course, we still have Thursday, but this class and the other class does meet next week. Your troubleshoot class that meets next week. Me and Nancy and Hoyt are gonna be on the 20th, 21st, 22nd. It'll be next Tuesday, Wednesday, and Thursday. I think we're not gonna have any classes next week. Now, you're still gonna get the same amount of time or class meetings as that we extended our class for one week. So it's still gonna be 8 weeks. It's just that we like to go to the 9th week and talk about that. So next week, not even online classes or anything, that classes actually, won't be in the room. This class won't be in the room, because this class meets on Tuesday and Thursday. But we're not gonna miss any time. So we'll actually, start that next class, Thursday's class, is that okay? We okay? And Thursday will be predominantly a lab day, so we'll make up for lab. Any questions on these 4 sensors that we went over? Is this all of them? No. So you might run into some that's a little different out there, but they all work on basically, the same principle. And, so we got one of these things up here, so we got 3 labs on proximity sensor. Most of y'all are almost through with the first one, right? And then we're going to start adding a relay to it. The 3rd lab is you're going to have to figure out how to basically design a circuit that uses proximity sensor. Now the next lab we'll deal with that we actually have to set on is that unlock distance and level sensors. Level we usually mean by the level of a gas and stuff like that, or a liquid. Of course, we already know this, right? We added this term right here. We need to understand this. I need to go back on the first slide and put this on. Because a lot of people, they use these interchangeably, transducers and sensors. You can get on the internet, you can type in transducer, you'll get about the same sites that you do when you type in one. Yeah, a sensor. It converts a form of energy into another, and that's what a sensor does, right? Usually, but sensor usually goes physical to electrical, and a transducer says it transduces or changes the form of energy. What we're doing is we're taking energy. By the way, y'all understand we don't create energy. What do? We just change its form. So we can't create energy. And unfortunately, there's no such thing as something to be 100% efficient. So what that means is your energy produced, what you change it into is always less than the energy that is required to do that. Right? You understand? Now we make. Well, we had a guy that came. Oh, I should say. Well, we had a guy coming in and interviewing for the job, and he was doing PowerPoints and doing the difference between DC and AC. And he said, AC, you can transmit AC with less power. What was wrong with that? Power is power, right? So like I said, if I turn on a 100-watt light bulb at my house, my power company has a 1,000 watt, 100 watt. So we're not changing the power, we're changing the voltage. So AC has the advantage is that we can easily step it up and step it down using transfer. So I can step it up real high for transmission, which causes the current to drop down, transfer that power, right? And then when I start getting close to your house, I start stepping the voltage down, which causes the current to go up for that power to make it work. So what advantage does low voltage have over high voltage? So what advantage does high voltage have over low voltage? That's current to produce the power, right? So as soon as he said that, the advantage of AC is we can step it up. As soon as he said that, as soon as he said AC requires less power, we can transmit energy with less power. that power changes. No, power in and power out. If we were in a perfect system, power in and power out would be equal, right? You understand that? But if we change the force, we lower the speed, right? You understand that? It's just like gears. So what we're going to look at now, we're doing what, level or distance? This is what we have labs on. So distance, the amount of space between two things. Level is the amount of vertical distance, height from ground or another state or understood state. The height at which one material stops and another begins. It's called the level. Okay, where I got these definitions at, probably Wikipedia. I'm not sure. I use Wikipedia a lot. You need to get in the habit of putting that on there. Huh?
Really close, it's not, anybody can change it. It's not a crazy, it's not a, yeah.
Yes, but it's a lot better than they used to. Used to, anybody could post. Now, basically, you can edit it, but it don't change until you have a group of people that goes out there and verifies the change. So it don't pop up there instantly anymore. Wikipedia has changed a lot. It was fun when it first came out, reading some of the stuff people said. Ultrasonics converts ultrasonic waves into an electrical signal and vice versa. Measures the time interval between sending and receiving the echo. The transceiver. So what's the term? A transceiver is a unit that contains both a what? Transmitter and receiver. We refer to them as transceivers. They can either be digital or they can be analog. So analog, of course, is going to give me the distance. Digital is going to switch at a certain. Right. What kind of question was you going to ask?
I have a transmitter receiver on a camera that I send a signal to the receiver on my little monitor. I have two antennas, one's the RX and one's the
One's a transmitter, one's a receiver, TX.
TX. But transmitter.
Yeah. So that's one-way communication. Anybody know what you call that? One-way communication? It's called simplex. So simplex is transmission in one direction, which is what your broadcast does. Then we have what we call half duplex. Half duplex is when we see in two directions but not at the same time. So if you ever did like ham radio or something like that, that's the half duplex. Used to, that's the way our cell phones were. Hand talking, now full duplex is two directions at the same time. So what's USB? USB is half duplex.
Yeah.
Because you can't have a 1 and a 0 on a wire at the same time. You only got two wires. So you have what we call a simplex system. Can be designed to sense distance, motion, level of a solid or liquid, speed, or direction. The only problem we have is limited by the what? Get a lot of reflection off flat surfaces, get less reflection off angled surfaces. Right? And this is one of the things that the military is doing to do try to make their planes not invisible. Well, they're not. They still can see them, but they just don't look like planes. I think the B-1 bomber actually reflects something like the size of a bird, or something like that. And the density, so that means you change the density. So the harder something is, the more reflection you get. The softer something is, the less reflection. So what does the military do on these planes to try to get them where people can't? They put a coating on them, right? It's a soft coating, and then they don't have any perpendicular angles anymore. What is it, F-111? That was the weird looking plane that couldn't fly without a computer. So these are ultrasonic. ultrasonics is becoming very popular on cars too, you know, where they sense, so my wife's saying when she's going back into somebody, it sends out signals.
That's what you control that sensor on.
Well, a lot of them have different things. A lot of them have camera systems on them too, which they actually see things. Your auto driving car and radar too. We've got to pay for sonar too. But these guys are usually fitted. But she's got signals that come on when somebody's just in their blind spot on the van, so you can see the little circles down there. It's got the
The worst thing what they have right now, keep your bright lights on and they shut off automatically when they sense another.
Oh, that's been around for.
Yeah, but them things never shut off. And you should behind you, look behind you, see lights flashing all the time.
Yeah, that's a new. So what's happening is they've got it on. And what's happening is they got it on bright, and when a car comes by, this way it dims it, and then when it goes back at bright, because your tail lights are not. I
Well, what do you want? What do you think? When you keep flashing your lights at me. Because I was flashing lights at the
you're still supposed to keep your lights on dim. Photoelectrics. We can use photoelectrics to sense distance. They call it triangulation. Transmits at an angle, and it measures the angle of reflected light to determine the distance. You understand that? Yes or no? You understand that? So what we have is normally what they have, and it usually only does it at street angles. So what we do is we shoot this at an angle. This is not a good picture. And then when it hits the surface, it reflects back. But if you shoot it at an angle, then the angle that reflects back would be proportional to its light. Huh? So if I come over here and shoot this thing and bounce it off the surface, and I shoot it at an angle, and it hits the surface, and then it's going to bounce back at the same angle, right? The angle of reflection, equal angle. But if I come over here and move this back, then this is traveling like this. It's going to travel, it's going to hit, and it's going to reflect back. But now the angle is going to change where it strikes up here. Does that make sense? And then we put a lot of these photo detectors. Each one of them would represent a certain angle. So which one it strikes would indicate how far the object is away. So this is working on the principle of a diffuse detector, but it's not designed to detect if something's present. It's designed to see how far it is away or how close it is, right? That makes sense? Well, a photoelectric distance sensor is what we refer to as triangulation. Y'all heard that term before? And where do you hear them talking about? You see a lot of these crime shows when they're trying to figure out where people are at. Right. So normally when you're moving through sales, especially in see like here, you're moving through multiple cells at the same time. And what they can do is they can measure your strength from what cell you're at, and then they can see where you're at, right? Does that make sense? It used to be, it could really be nice. Now, of course, now a lot of our phones have GPS on them. Yeah. It's not extremely accurate, but it's pretty dang accurate. You turn that on. So you see these people that post where they're at all the time? I don't know. They do that on NCIS, I think.
No, I mean, like, they actually have something that sends it to the phone that comes backward.
Yeah, they can, that person of interest where they had that application where they could just get by the phone, pair it with it. So Time of flight photo sensors. So light moves at a certain speed. If we time the amount of time it reflects back, then we can literally calculate the watt distance. So that's what they're doing. Speed of light is roughly 300 million miles per second. And then you take this, right, understand, you divide that by 2, and this will give you the amount of time. And you multiply that times C, and that would give you the distance. Now this guy right here is going to require some computation. But this is basically, a lot of your police are using this system right here instead of using radar. And why are they doing that?
I got hang out the back window time.
Why are they doing this? Yeah, the radar guns can be detected because it's sending out electromagnetic waves. It's hard to detect light because we're constantly on light, right? So a lot of your police are using these time of flight sensors now. And what they do to calculate speed is they'll send out one pulse, measure the time, and they'll send out another one, measure the time. They know the distance that you travel within that amount of time, then they can calculate your speed.
Still those, see two little strips across the road, or counting cars, no, I never did.
Normally those are usually pneumatic. And what they're doing is they're trying to figure out the traffic flow. You know, depending on what they're going to do with the road and all that other kind of stuff. And they do that all the time, whether they're going to make it bigger or smaller, or all this other kind of stuff that they require to do. Normally they'll put 2 of them too. They'll put 2 that's close together. And I think what that is just for duplication. I'm not sure why they have that. Even though they could probably use that to sense. You can't really do it to sense speed because all your vehicles have different wheelbases. So your speed would vary between the distance between the front tire and your back tire. So I think what they do that for is they do it for duplication in case one of them doesn't trigger exactly right, the other one probably will. I don't know what he's talking about. Y'all see those?
Yeah, they get an average.
Yeah, they probably just add them together and divide it by 2. And that's all they're trying to do is try to figure out traffic flow problems. Yeah, during the day. So usually they'll leave them up about a week. Sometimes they leave them up longer than that. Ultrasonics. Of course, it's pretty obvious how these things work. What do? They shoot light, they shoot a sound beam out. So these guys here work on basically the same principle. These are using the speed of light. The other one is using the speed of sound. They shoot a pulse out. Most of these ultrasonic sensors, a lot of times you can hear them clicking. So they're actually clicking when they send it out. I think you can hear that on one of our robots over there. So okay, ultrasonic level detectors. These are what they use down. What's nice about these are non-contact. The actual electricity is outside of what it's trying to measure. So we can use these to measure the level of flammable. Okay. This is what they use down at the tank farm down in Helena, the gas tank farm. So of course these are the kind that we're going to use. These are very, 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 very popular. These are discrete or visual types. So notice what we have here. And this is a level detector, but we're combining it with a limit switch. This is what I told y'all the other day. Sometimes we combine 2 sensors to perform one function. But can you see how this would work? Pretty straightforward, isn't it? So what we have is we have a cam, and then a limit switch that's got a roller on it. When the flow goes up, it causes that to trigger I think ours uses what we call reed switch. Ours uses a reed switch stone magnet. This right here is what? It's go through the beam, so when the liquid comes out, it blocks the beam, and now we know when it's at a certain level. This right here is a resistive probe where we actually put a voltage on here, and then when the liquid comes up, it kind of changes the water between them, changes the resistance, and then of course now it can measure the level. The airplanes use, I don't know if this book covers it or not, but it should. Airplanes use capacitive sensors, which work on the same exact principle. So they use capacitive probes, at least the airplanes that I worked on. First of all, we don't like to use floats, right, because the plane. So the way a capacitive works is we have two plates, and if you remember, what determines it would be the size of the plates. You'll remember? What else? The distance between the plates. And the dielectric constant, good. So if we put a frequency on this thing, so these things here operate off AC, and then this fluid comes up here and starts going in between the plates, what are we going to change? It's going to change the dielectric constant. And how much you have in there would depend on the dielectric constant, which is really, really neat. So that means the opposition of the plates would change, and it would be directly proportional to the fluid you're trying to measure. And what they would do in the airplanes is they would have, we had what we call wet wing planes. Well, that was not true. The P-3 Orion had a belly plane, about 50,000 gallons, 5,000 gallons, 50,000 gallons. And then I forgot what the wings would hold. I think it would hold about 2,500, 2.5 thousand a piece. It's big plane. That's 10,000 pounds of fuel. They weighed in pounds. And then they had these passive sails. They were on the bottom of the wing, on the top of the wing, and they just summed them all together. So no matter what attitude the plane was at, you got the sum of all of them and gave you the right amount of fuel. Those planes could be flying like this, like those jets. You know, those jets, they fly upside down and sideways. You don't want like on our cars use a float. So, you know, you're sitting on a hill, that's going to show you one thing. You sit flat, so that's has the problem. People think they have a lot of gas and they're on the hill, and then they get down here and they're out of gas, right? We did this. There was a hill on 157 going up to Florence, so Molson Joe, before you get to Molson. That thing was so steep that I used to run it all the time. You'd see big trucks sitting on the side of the road where they start up that hill, and all their gas would move to the back of the tank, and they couldn't make it up the hill because they run out of gas even though they had gas. You used to see that big truck stop down in Milton was full of trucks that go out and they'd fill up before they did what? Y'all know what? Y'all ever been up to Milton, up to Florence, that big old hill? It's 4 lane now. When I was there, it was 2 lanes. I used to work on a, huh?
Don't own a gas station down there.
Coming downhill, they didn't have any problem going uphill because they could coast till they hit the ground. So these are the probes that they're talking about. The ones we got is ones with the lab on. They both work on the principal plate. I didn't follow my way. So we have a piece of foam under here, so make sure after you do the lab, you put it back under there and what the and I'll pass this around. So these are the two level sensors that we're going to use. I got another application that did it full screen, but now I can't get it to load back up. So this is the other application, and it's up there, but I can't get it to come up. It's real neat. It's full. It does it full screen. Huh. Let's take a break. I'll try to figure my cameras out. Sensors that we're going to be doing lab on. Now, one thing new about the new panels is they don't give you the little diagram up here like they do in motor control that shows you how to hook things up. So basically, it's up to you. A lot of times it's pretty straightforward on that. So you can see this liquid level sensor comes down to 1 and 2, and then this one right here drops down to 3 and 4. So most of the time it's pretty easy to figure out. There's a piece of foam under this one. So these are digital, and they use floats. But notice they're non-contact. So what do you think they're using? So they do come in contact with the liquid, but the sensor itself is right in here. And then up here is a magnet. So what do you think they use? You have the reed switch. So that's what they use. And this is the same thing true here. Y'all don't take this off, but you can actually see the two magnet bars right here. And then the reed switch is actually in here. So when these things move, when it hits a certain position, the reed switch closes. And when it drops down, the reed switch opens. Right? So ours are digital in nature. So these are actually measuring a level, but it's measuring a level when it gets to a set point. So after y'all do the labs on proximity, and we looked at a lot of proximity sensors. The only two that you're going to use is what was the first one on? It was on what type of sensor? First, what capacitive? Inductive, right? You just put a piece of metal up there. You could put your hand. If it was capacitive, you could put your hand up there and you could have got close to it and it would have walled. It would have triggered it. Inductive though, you had to put a piece of what? Had to put a metal up there. And I think if you got your first part, I got an aluminum key and I've got a metal fault bar. The metal's real thin. The aluminum I had to get almost right up against it, but it did find it. And then the steel one, it was a little old thin thing. I can get it up there fairly close and it picks that up. So inductives will pick up any metals. It's just that my foot gets that. Just that the distance it picks it up varies with what type of metal it is. But normally if I've got that in the industry, I'm looking for what? A certain metal. Like if I'm doing dog food cans, then my dog food cans will always have the same consistency, to count, so we don't have any problem. But the capacitive sensor will find glass, right? So this is going to use a reed switch in here, and so these are not solid state, so they don't have to be powered up. If they did, we would require at least 3 wires, right? These are normally open switches in here. So if it's got a single pole double throw or two different switches in there, then we'd have at least 4 wires. So this is one of the problems we have with these sensors. Is the number of contacts that's available, right? So if I need this in, 4 or 5 different lines in my control circuit, what are we gonna do about that, guys? It won't switch. I gotta get. So what would we do about that? So let's say I need 4 contacts off of this sensor, and this sensor only provides 1. Yeah, we would connect it to a control relay, and then we would get the multiple contacts off the control relay, right? That makes sense. That makes sense. So you'll see that do a lot. It's very unusual for solid state sensors. In reed switches, we've only got 1 set of contacts. Solid state sensors, you're either going to output a signal or the inverted signal. They still call that but we'd have 4 wires. So basically that's it. You got only solid state sensors, but it's no big deal. Is that you just use a solid state sensor to pick up a relay, right? And then use the contacts off the relay to control as much as you want. Well, a lot. Then we could use the contact off that relay to pick up another relay, right? If we needed tons of contacts. But these guys right here are pretty straightforward, The ones we're using would fall in which category? Would be this guy right here. Except instead of having a limit switch, we're using a magnetic. You see how these would work? Yes or no? These are digital. This right here would be analog. So these wouldn't tell me. This right here would not tell me what the level was. It would just tell me when the level was at a certain point. Okay. What's that?
It's exactly what project I was working on a long time ago. I was running a temperature system where it can test saturation level of the pot. So you don't have to worry about watering it. Just tell the computer to set on pump water into the pot and then on tomatoes.
Now you can make these basically, guys. All you have to do is just put 2 pairs of bare wires down each side of the tank and put them together. Now these are going to be pretty high resistance, but depending on the liquid, how much resistance is going to vary. But very few. It would have problems with distilled water, but anything that's not distilled, then it's going to change its resistance depending on how much water comes in between those two electrodes. And the capacitive uses the frequency.
How would it be
What's that?
the photosynthesis? How would it be without the water?
Well, if it's not perfectly clear, it's going to get a change depending on the distance, right? So when it goes through the water, it's going to have a tendency to diffuse. So that means not as much light will get through. It's hard to have perfectly crystal clear water. So if it's not crystal clear, right, you understand, then the light is going to diffuse while it goes through the power. What you receive is not going to be what's being transmitted. So because you lose power to do that. So if you have a sensitivity adjustment, which most of us do, then you could adjust it to sense almost all of it. It's just like photo optics have problems. Photo optics have problems with clear. Well, that means, what would that mean there? Well, it means if I could not use that sensor, I'd have to use ultrasonics, or I'd have to use something else. I could use capacitive. Capacitive sensors, would change its dielectric. So we could use capacitive sensors no matter what the purity of the water was. So, but capacitive sensors means we're going to have an oscillator. We can't put DC on a capacitor. We have to put AC because it works. What's nice about a resistive sensor is that we can put DC or AC on it. But that's why we have so many different types of sensors. So if one don't work, then odds are we got another one that we could work. Ultrasonics is going to be more expensive. But ultrasonics might not work in some situations, right? So if I'm trying to pick up something that's very soft and all kind of weird shapes, and ultrasonics is going to have a problem. But I might be able to use this guy, or I might be able to use this guy, or I might be able, this guy would work with me. That I know of. And this is basically the same thing. Another thing we could use, which is always up here, we could put load cells. This is what James was talking about. They use a lot of these where you get a big old hopper, and you're trying to see how much material you have in there. And if you know the weight of the material, then you can use load cells and just measure the weight and translate that over to what? Over to the load cells are very popular. Electrodes are very popular, either R or C, like airplanes use C. They use capacity. Ultrasonics, we could use pressure. So how much liquid we have up above, if we put a pressure sensor down here, the weight of basically how much pressure that thing generates would give us the level. But that would vary with density too. But if I'm measuring the same liquid or the same material, then I can do weight or I can do pressure, right? If I know how much weight how much it weighs per cubic foot, then I can figure out what the actual level is by just measuring the pressure or measuring the weight. But yeah, still they use this a lot. Big old poppers, because normally they're using solids. So solids would not work with, or powders, solids would not work with clay, right? They would work with what? Ultrasonic. They wouldn't work with this because the pressure was very. This wouldn't work, but these guys right here would work. So if I was trying to measure iron ore pellets, and I was trying to see how much iron ore I had out there, then we could use what? We could use weight. So they do a lot of that stuff. It used to amaze me just to make iron, what's required to make iron. So, what's so neat, number 8 blast furnace had about 6 different hoppers out there. And they would mix up what iron they would shoot for, and that computer would automatically dump it out on a conveyor belt and then mix it up and pour it in the top.
I bring 130 car train.
Oh yeah.
That train pushes around like that.
Yeah. I got some. They depend on rail out there. And it's still a lot.
It's that cloud because the winter up north, they can't get any. Some of the rail stations down up north. They can't go on one time.
So the only mill running out there now, a full steam, is the pipe mill, right?
Right. I haven't talked about it.
Usually we get a little feedback. But, somebody said they were going to start building the arc furnace out there, but I ain't heard anything about that either. I don't go up that way much either. Oh yeah, I was at CMC Steel. Well, they have 3 now, I think, big arc furnaces. They used to have 2 when I went. You ever heard when these high tension voltage lines come in contact with each other? That's what you get. Okay, guys, so we should be okay. So as soon as we finish that lab, then we should be able to move directly into this one. Which ones we're going to use? We're going to use the one kind of like this one right here. Huh? Yeah, well, what we're going to do is of course, we need to get some cups. I usually have to try to bring some styrofoam cups in. Well, not really on this one. So this one we can actually do we can simulate. So you take your finger to
Get the water.
yeah, and the way it's written, it says, okay, we want this up to plug this level, we want to simulate that. Later on, we're going to get into temperature sensors. And temperature sensors, we're going to use hot water and we're going to use ice water. So let's go down to the cafeteria and pump some ice. Anyway, And then we can go down to the men's room down there and hot water.
No, they don't. I don't think they have hot water.
Well, that's about
You're
somebody-
I might switch one over and don't work.
You have to leave it open pretty good, the boilers are not real close. I think they've only got one boiler that's very. I'm not saying, last time I checked it, it was there. It hadn't been.
You probably have to do water.
We could, I might look at getting
All they do is just put
they're not very expensive. We might look at trying to get one for the lab induction boiler. Real power. I've seen those things. They work off induction. And they'll boil water. That's what they had in the hotel rooms in Germany. They provide to you. You just plug that sucker in and turn it on, and you're talking 20 seconds. They're very, very, very popular. Also, so any questions on these? So we talked about what? So now we know the meaning of life, right?
We know the truth.
We used to watch Night Court, and one of the guys said, any questions? And one guy raised his hand and said, what do you need? He said, why is the sky blue? And the judge said, well, if it was green, nobody would know where to stop cutting that grass at. No, it's not. It was one kind of like little kids would tell. They tell these jokes. So what have we covered so far? We covered position, we covered speed, force or weight, right? What else have we covered?
Can't really say flow rate, but
I did flow. Flow is one of them we'll have to talk about. So flow rate we haven't looked at. Of course, light. We talked about light.
Right, the transition.
And then level distance. Because proximity too, proximity sensor.
you could really count moisture, but you are talking about the flow sensor, so.
Moisture sensors usually is kind of like humidity sensors where it senses the amount of moisture.
Yeah, there's a tiny one you know.
Yes, so and it usually works on the principle of R.
Yeah.
So or capacitance, which is